I just think that there have to be reasons that you get up in the morning and you want to live. Like, why do you want to live? What's the point? What inspires you? What do you love about the future? This is not, people are mistaken when they think that technology just automatically improves. It does not automatically improve. It only improves if a lot of people work very hard to make it better. And actually, it will, I think, by itself degrade, actually. You look at great civilizations like ancient Egypt, and they were able to make the pyramids, and they forgot how to do that. And the Romans, they built these incredible aqueducts. They forgot how to do it.
Good morning, everybody. I am Adrian Ardaiz, and today I'm going to defend my thesis, Design Analysis and 3D Printing of a Medium-Sized Metal Component. This is a case study on topological optimization. First of all, I'm going to explain you this term, topological optimization, so that you all can understand the goals we set for the thesis. Afterwards, I will explain the methodology we have followed, and finally, we will obviously see the results. Imagine all the chairs at your house are like this one. Must be heavy for sure. Imagine every day moving it from one place to another. That must be a nightmare for your back. So one day you decide you are going to remove as much material as possible, but obviously you want it to stand your own weight. So you start removing materials from one place and another, and every time you cut material, you sit on the chair in order to ensure that it still supports your weight, until you finally get to this design. A chair much lighter, but that still supports your weight. Basically, that's topological optimization. Now imagine extrapolating this concept to other industries, such as the automotive industry, like Formula 1 cars, or even structural designs, as you can see in the pictures. Obviously, this technology holds a great potential. In this research, we have achieved optimizations of up to 50% and up to 75% mass optimizations. Now, a lot of optimization, a lot of potential, but you may be thinking, how on earth are we supposed to build that shapes, that complex shapes? At this point, we introduce this word, symbiosis. Same as the sharks with the remoras, this basically means that the two subjects contribute with the advantages of each other. Topological optimization has a very symbiotic relationship with 3D printing. Probably all of you already know this technology, but I'm going to explain the basics of it. Traditional manufacturing methods start usually from a big chunk of material, and we remove parts from the material. However, in 3D printing, it's all the way around. We start from little pieces of material, and we add them together in layers until we get to the final design. This not only enables us to reduce the losses of material, but as well it enables to create these complex designs. Now we all understand this technology. This is the two case studies we have studied on this research. First of all, a year from the company EMPA, and then a component of a mold from the pharmaceutical company Thinfa. In this investigation, we have set two main goals. First of all, to study the feasibility of topological optimization with 3D printing, and the second goal was to reduce this component as much as possible in weight. This is the methodology we have followed. We already have the files of the components, so we directly introduce them in a 3D computer-aided design software, which is SolidWorks. This software offers a lot of tools, however, we have focused on its simulation module, specifically on the topology study. This is where we go from the initial component to the already designed component. But as we have said, we also want it to 3D print it. So we need an intermediate step, which is the Cura software. What we do in this software is kind of create the instructions that the 3D printer will understand. As well, we set the parameters of the 3D printer. And finally, we print the components. But okay, so far, we don't know how we are optimizing the components, because imagine, we have this component. Where will you start removing material from it? Personally, I will have no idea. Luckily, this is not our task. What we have to do is to input the constraints. These are the forces that the component must stand, the preserved areas, and some fixed parts. Afterwards, we input the goals of the simulation. Once we have input all the constraints, it's time of the algorithm to come in. The algorithm is the one who takes the component and optimizes it. There are a lot of types of algorithms. However, the most common one is the finite element analysis algorithm, which is the one that in an either constructive or destructive method reaches to the solution. My professors and I thought it was a very good idea to kind of carry out a minimum viable product in order to take a first grasp of this technology. So we study experimental specimens. We design them according to the ISO standard. As we have said, we input all the constraints, and we carry out several simulations, obtaining these amazing results with up to a 52.7% mass reduction. Now, let's go for our first case study, the year from the company EMPA. We are going to input the constraints, as we have said. It is a year, so it must move around its axis, hence, we establish as a fixed part, the axis. Then it has the forces on the teeth. Obviously, it has many other residual forces. However, this is the main one. That is why it's the only one we took into account. And we define the teeth as preserved areas as well. With this component, we have one problem. We have one problem with the computational power, because that component is 1/2 scale. So in reality, it's kind of much bigger. And the computer wasn't powerful enough, because when we run the study, the algorithm creates a mess. The finer the mess, the more detail we'll have the solution. However, the more time it takes for the simulation. On the contrary, the coarser the mess, the quicker the simulation, but the less detail. This is me on a computer room carrying out several studies at once. I studied the entire year as well, a quarter of a year, 5 teeth, and 1 tooth, because I wasn't obtaining any results. Afterwards, I changed the meshes to coarse meshes for the problem I have told you. And after waiting 1, even 2 hours, I started obtaining some results. With the entire year, with a force of 1,000 newtons on its teeth, I obtained this result with a 49% mass reduction. Pretty unbelievable, because not only we obtained it theoretically, but as well, as you can see, we were able to print it with a 3D printer. But 1,000 newtons is not a really big force comparing to the real working conditions. That is why afterwards we carry out a study with 100,000 newtons, which is a more really realistic force, obtaining as well an astonishing 25% mass reduction, with a kind of similar pattern. In the studies of a quarter year, we also obtain pretty good results. Obviously, it is just a quarter of a year, so we have to create an assembly, joining 4 parts of them. And we obtain a 75% mass reduction. However, this year has 50 teeth, so a quarter of a year is not a multiple of that number. So when we create the assembly, as you can see, there are some little failures on the joints. That is why we didn't carry on with this research. The 5-teeth study didn't yield any good solutions, but the 1-tooth study, we can see a very interesting thing, that even the inside of the teeth can be optimized. What does this mean? That if we have more computational power, maybe we could even study the entire year, and instead of just optimizing the inner hole, we could even optimize the inside of the teeth, translating in an even further reduction in weight. And last but not least, the component of the mold. Okay. This is a real scale component of the mold. We are talking about the dark gray area. This component, its task is to hold the neck of a bottle, as you can see here. Here will be the neck of the bottle, and a strike of air inflates the bottle. We are only studying 1/2 because they are symmetrical, and then they are joined with a closing force. So we input the constraints, the fixed parts, the preserved areas. Obviously, here is where the neck of the bottle is held, so we don't want that part to be removed. That's why we set it as a preserved area. And the forces. In this blue part, we have a 500,000 newtons force in this blue area. On this red part, if you can see it, we have a 40 bar pressure. That's the pressure it's applied in order to inflate the bottle. And finally, we have some residual forces on the up and down surfaces, just due to touch with other components. Here you can see the mesh that the algorithm creates. And we obtain an 11% mass reduction. One more time, we were also able to print it. Again, proving the feasibility of these two technologies, additive manufacturing with topological optimization. An 11% mass reduction may not seem as astonishing optimization as the ones before, that were of 50, even 75%, but we have to take into account that the force applied on the blue area is the same as if 8 elephants were standing here, literally. So we think that an 11% mass reduction is a pretty good solution. If you want to see them. All in all, I hope today you have taken a better grasp of what is topological optimization and the great potential it holds together with 3D printing. We set 2 goals that were to prove the feasibility of these 2 technologies together, as well as to reduce the weight of these 2 components as much as possible. I have shown you the methodology we have used and the great results we have obtained, with a 52.7% mass reduction on the experimental specimen, a 49% mass reduction on the year, and a final 11% mass reduction on the component of the mold. That's all from my part. Thank you everyone for coming.